Hello, everyone. My name is Keaveney. I'm an undergraduate student at NC State University studying meteorology and applied math. And I'm going to be talking about this research project that I designed and I've been working with my mentor, Gary Lackman, on for over a year, modeling the meteorology of Jupiter's Great Red Spot. So this is the Great Red Spot. It is the oldest and largest meteorology phenomenon that we know to exist in the solar system. It is basically just a massive storm in Jupiter's southern hemisphere that's been going for over 200 years, maybe as long as 400, 500 years. So it's a really old, really large storm, and it is similar in basic meteorology terms to a hurricane in that it is a really large rotating storm with very strong winds. However, there are some notable differences. First of all, hurricanes on Earth rotate clockwise in the southern hemisphere. They have the strongest winds in the center, and they are low pressure systems. The Great Red Spot, on the other hand, is a high pressure system that rotates counterclockwise, and it has the strongest winds in an outer ring around the Great Red Spot rather than in the center. So very important distinguishing features of the Great Red Spot compared to a hurricane. And we know a lot about the Great Red Spot. We know obviously what it looks like. We have tons of pictures of it. We know generally what the dynamics of the Great Red Spot look like. But there's one important thing that we don't understand about the Great Red Spot. So this is what the spot looked like in 1974 when we saw it with the Pioneer 11 spacecraft. This is what it looked like in 2000 when the Cassini satellite flew by. And this is what it looks like in 2021 when the Hubble Space Telescope took a picture of it. And as you can see, it has gotten a lot smaller. So the oval I've imposed on the images generally corresponds to the size of the 1974 Great Red Spot. And clearly it is getting smaller. This has been documented by scientists for decades. We know this is happening. We just don't know why. And that is a really interesting meteorology question. Why is this, huge storm that's lasted for so long, why is it now getting smaller? And we don't know why. And the goal of my project is to figure that out. So what I want to do is take meteorology theory in the form of these equations applied through a computer model, specifically the explicit planetary isentropic coordinate model, which is developed by a bunch of really smart people with the help of NASA in the late 1990s and early 2000s, and apply that to the atmosphere of Jupiter and the case of the Great Red Spot to try to replicate what we've observed with respect to the storm's longevity and its dynamics. And I've made some progress so far. It is a really challenging thing to do, as we've discovered. So this is a simulation of eddy potential vorticity development over 2.5 days. Basically, what are the clouds doing? Is there rotation in the system, etc., on the order of a few days? And as you can see, the answer is yes, there is rotation. There is counterclockwise rotation. That is, the storm is also drifting westward, which the Great Red Spot does as well. But it doesn't look exactly like the Great Red Spot. It's not this oval shape that we have come to know and love. It also dissipates after a few weeks. And that has been the really interesting result so far, is that we are having a hard time getting a spot in this model to stay and be stable on the timescales that the Great Red Spot has been stable in Jupiter's atmosphere. And so that just goes to show the remarkable challenge that this project that we're taking on is, and how complex of a storm the Great Red Spot is in general. So the next steps for me are to try to make this spot that I've been able to generate look more like the Great Red Spot, in hopes of replicating more of the dynamical structure that's allowing the storm to be stable. And then once I have done that, extending the duration of the simulation to hopefully account for and test for the longevity of the spot. So these are all the lovely people I would like to thank, in particular my mentor, Gary Lackman, as well as Anantha Iyer, Raul Morales-Uberias, Tim Dowling, Ramana Sankar, and Sean Brushaber, who've all collaborated and given me advice throughout this process. I'd also like to thank Dr. Lisa Lowe and the NC State High Performance Computing Services, who helped us compile and run EPIC a number of times. In addition, this project was supported by the North Carolina Space Grant through an undergraduate research scholarship, so big thanks to them as well. And these are my sources. I appreciate your time, and I hope you enjoy it.